Going on, guys? Here we have lens combination of two converging lenses, and the focal length of the first lens is 30 centimeter and the focal length of the second lens is given by 20 centimeter, and the object is placed in between the focal point and the lens, and the distance of the object one, actually just one object, right? The object is 15 centimeter, and the question here is asking us to find out the image distance of the first image and also image distance due to the second lens. So this one is due to the first length and this is due to the second length. Now let's see how we can figure it out. Now to do that, first go ahead and draw our ray diagrams. So first one is for the converging lens. First we draw a line that is parallel to this normal. So this is going to go like this, and after it hit the lens, it's going to go through the focal point. So here it's going to go through this one, right? So this is going to go like this. So let's call this is focal point. And then we have to go, the next line should go through the focal point, but since we have the focal point after this one, what we have to do is we have to extend a line from this focal point. So if you extend like this, it's going to go like this, right? And it's after it hit the lens, it should go parallel to this normal, but this lens should be a little bit bigger. Now let's erase this one and draw this one a little bit bigger, right? Okay, now we have a bigger lens, and this also a little bit bigger. Okay, so now let's draw the diagram. So the second line is going to hit the lens. After it hit the lens, it's going to go parallel to the normal. So it's going to go like this, right? So this is our second ray. Now where is the image is going to form? So according to the observer doesn't see, like the brain doesn't consider this is reflected, like this one is refracted. According to human brain, this appears to be coming from here, right? So when we extend this one, and also when we extend this line right here, this will meet somewhere. So that's going to be the image distance. And if you draw a line like this, that's going to be the image distance. Here it appears to be exactly in the focal point. Now let's see mathematically it makes sense. Now to do that, I'm going to use this equation. The first equation, s prime is equal to sf over s minus f, and s is object distance, s prime is image distance, f is focal length. Now the object distance is 15 centimeters, so this is going to be just 15. But before I go and do that, I identify this one as S1 because we are going to deal with two objects. Like the image of the first one is going to be the object for the second lens. So this is S1, object 1, and also image 1. S1, F1, F1. Okay, so S1 is 15 centimeter, 15, and the focal point of the first lens is 30 centimeter. Focal length of first lens is 30 centimeter, so this is going to be 15 times 30, and in the denominator we have object distance minus the focal length, so that's going to be 15 minus 30. 30 times 15, that's going to give us 450. 450 divided by 15 minus 30, that's going to be negative 15, and if you divide these two together, that's going to give you negative 30 centimeter. Since we are having a negative value, this means this is virtual, and it makes sense because we are getting the image in front of the lens, so this is definitely a virtual image. Now also to prove this one upright, we can use this magnification equation. So magnification equation is m is equal to negative s prime over s, and s prime is image distance, that's what we found out right here. So this is going to be minus 30 divided by the object distance, that is 15. So 15, and that's going to give us 30 over 15, that's going to be equal to 2. So the image of this image due to the first lens is going to be 2 times bigger than the object. That's what it means, right? And also this is upright because we are getting the answer in positive. So this is going to be an upright image. Now let's look at what's going to happen to the next one, like when we use the second lens. So for the second lens, the first image is going to be the object, and we have to know what is the distance from the lens to this object. And we know we found out that image is 30 centimeter from the first lens, and we know the image like the distance between the lenses is 10 centimeter. So 30 plus 10, the totally we are going to have 40 centimeter, right? So 40 centimeter is going to be the object distance for the second lens. Since we are having the object in front of the lens, this is going to be positive. So we can put positive 40, right? Now let's go ahead and calculate the image distance for the second one. And let's see. So second one, we are going to have S prime is equal to S times F over S minus F. And S is object distance. We found out that is 40. This is plus 40 because it's in front of the lens. So this is going to be plus 40. And then we are going to multiply by the focal length of the second lens, that is 20. Right? And in the denominator, we are going to have S minus F. That's going to be 40 minus 20. 40 times 20 is 800. Divided by 40 minus 20, that's going to give us 20. And that's going to give us 40 centimeter. So the second image distance is in 40 centimeter. And since we are getting the answer in positive, so this is a real image. This should be behind the lens. So the image should be somewhere here. We know that f2 is 20 centimeter, but the image should be somewhere here, right? Now to find whether it is upright or inverted, we can use the magnification equation and figure it out. So m is going to be negative s prime over s, and negative s prime we found out right here, that is 40. And this is let's mention this one, this is real, right? Real, and this is 40, so this is going to be negative 40 over the object distance. We found out that is 40. So negative 40 over 40, so that's going to be negative 1. So this means this image is inverted, and this is actually exactly as the size of the first image we had. So this is related, this magnification is related to the first image because we are treating first image as the object. Now if you want to know what is the magnification related to the object, we have to use the m total equation, that is mt magnification total is equal to multiplication of these two magnifications. The first magnification we got is 2, right? So we put 2 right here. Let's put generic equation, that's going to be m1 times m2, and we found out m1 is equal to 2, so this is going to be 2 right here. And we know that this is, let's mention this one m1, and this is m2, and we found out m2 is negative 1, so this is going to be negative 1 right here. And the magnification is going to give us negative 2. It means the related to the object, this image, the second image due to the second lens is going to be 2 times bigger of the first one, and also is going to be inverted. So that's what we get from this equation. I hope this helps. Thanks for watching.